All right, guys. Welcome to today's class. Today's class we want to talk about Chem 132, the first topic in Chem 132. By the way, Chem 132 is a course code for organic chemistry. Introduction to organic chemistry precisely. Now, Chem 132 is actually organic chemistry course offered by year one student of the University of Port Harcourt. Right. So I want to talk about Chem 132, Introduction to Organic Chemistry. I know a lot of us, watching this video had a very poor background in organic chemistry, but I just want to assure you that you've come to the right place. By special grace of God, I'm going to help you guys overcome the challenges that, Chem 132 has actually posed on you guys. All right, guys, before we actually dive into the class, please subscribe to our channel. Just hit the button below. All right, like and comment. Okay. What exactly are we going to be looking at here? We're going to talk about introduction to organic chemistry, organic compounds, catenation, and elemental analysis. All right, so first you may want to ask yourself, what is organic chemistry? Organic chemistry is a branch of chemistry that studies organic compounds, all right? So basically carbon-containing compounds. Okay, so what are organic compounds? Organic compounds are compounds. These are compounds that comprise of carbon, and other elements. Now, these other elements we're talking about include hydrogen. Now, hydrogen is compulsory. Hydrogen is compulsory. Now, if it contains carbon and just hydrogen, we call those type of organic compounds. If it contains carbon and just hydrogen, we call those kind of organic compounds hydrocarbons. Hydrocarbons are basically compounds that contain just carbon and hydrogen, right? Now, in addition to carbon and hydrogen, organic compound can also contain other elements such as nitrogen, sulfur, halogens. Now, halogens we have chlorine, bromine, iodine. All right. So in case somebody asks you, what are the compulsory elements that has to be present for a compound to be called organic? The two compulsory elements that has to be present for a compound to be called organic are carbon and hydrogen. Now, example of such compounds, which are the hydrocarbons. If I have CH4, this is methane. If I have C2H6, this is ethane. I have C3H8, this is propane. All right. Now, other elements, in addition to carbon and hydrogen, we can also have, sorry, I was supposed to add oxygen here. We can also have oxygen present in an organic compound, nitrogen present in an organic compound, sulfur, and of course, halogen. Now, example of organic compound that contains oxygen, we have CH3, CH2OH. Now, this is ethanol. Example of organic compound that contains nitrogen, we have CH3, CH2. Now this is amines. Example of organic compound that contains sulfur. Now this is thiol. Right? So this is alcohol, this is amines, and this is thiol. Right? Okay. So having introduced or having shown us what organic chemistry is, we said organic chemistry is a branch of chemistry that studies organic compounds, that is carbon containing compounds. Okay, and I gave us an example. Now let me tell us this. Not all carbon containing compounds can be considered organic. Example, CO2. Yes, it contains carbon, but CO2 is not considered organic. Why? Because there is no hydrogen here, right? But however, if I introduce hydrogen to this compound, this can be considered organic compound. So I believe we all understand the concepts behind this. So the next thing we're going to be looking at for is the first organic compound that was actually synthesized, right? What is the first organic compound? Because we've seen organic chemistry, we've seen organic compounds, right? The next thing we're going to be looking at for is the first organic compound that was synthesized, all right? The first organic compound the first organic compound to be synthesized, let's put it this way, the first organic compound to be synthesized was urea, right? It was urea, spelled as this. Now, urea was obtained from ammonium cyanide. Now, this is organic. Now, urea was obtained from ammonium cyanide, which is inorganic. So in case of exams, they might ask you to give the name of the first organic compound to be synthesized and also give the structure, the molecular formula, and it was synthesized from what? Urea was the first organic compound to be synthesized, and it was synthesized from ammonium cyanide. Now, what is the reaction that gave rise to this? Now, this ammonium cyanide, we have NH4CNO. Okay, when you hit this guy, now this gave rise to NH2C. So in terms of molecular formula, so we have ammonium cyanide, and this is urea. Now this is inorganic and this is organic. Now it's important for you to know that in terms of molecular formula, like the number of atoms of each element, they are the same. This compound contains elements nitrogen, elements carbon, and elements hydrogen. How many nitrogen do we have here? Is 2. How many carbon do we have here? Is 1. Hydrogen is 4, and oxygen is 1. So this is basically the molecular formula of this compound, right? Which of course you can see that this is also having the same thing here. So urea was the first organic compound. Now this is organic and this is inorganic. Okay, so you should take note of this just in case of exams. Urea was the first organic compound to be synthesized from ammonium cyanide. Now the next topic we have here is catenation. Now catenation is actually a property of carbon. Now why are we discussing catenation in organic chemistry? I'll tell us. Now if you noticed, all organic compounds must contain carbon or will always contain carbon. But the interesting part or the interesting fact about organic compounds is that carbon will always be the central atom, right? Not just any atom can be at the center of organic compounds. It must always be carbon. Why? Because carbon possesses some properties that makes it outstanding. And one of those properties is the ability of carbon to form a long chain, right? I know you've seen carbon forming C20, C10, C15. That is, you see this, and so on and so forth. Now, not all elements can form a stable long chain and still be very strong. So that is one thing that makes carbon outstanding. All right. So the ability of carbon to form a stable long chains with itself and atoms of other elements is what we know as catenation. And this is the reason why carbon is always the central atom in all organic compounds. So we say catenation is the ability of carbon to form a stable long chains with itself and atoms of other elements. So catenation is the ability of carbon to form a stable long chain with itself and atoms of other elements. And remember, it is because of this property that makes it possible for carbon to always exist as a central atom in an organic compound, right? And not just that, carbon is tetravalent in nature, which means carbon can only hold maximum of 4 bonds, right? The maximum number of bonds carbon can take is 4 bonds. Now the 4 bonds can be in a single bond. You can never see carbon hold more than 4 bonds in any organic compound. So please take note of this. So that in case you see a compound where carbon is having 5 bonds or 3 bonds, it is wrong. Carbon must always have 4 bonds. Either we have 4 single bonds, like in this case, or we have something like this, right? In this case now, we are having 1 double bond and 2 single bonds, or we have 1 triple bond and 1 single bond. If you count the total number of bonds or the lines here, it is still 4. 1, 2, 3, 4. Just that these two is forming or is coming together as a double bond. Or we can also have something like this, where carbon forms a diene. Here, carbon is holding 4 bonds. So please take note of this, that carbon can hold maximum of 4 bonds, right? So as you're learning this in here, as we are moving forward in this course, you can never see carbon hold 5 bonds. If carbon is holding 5 bonds, it is wrong. If carbon is holding 3 bonds, it is wrong. The maximum number of bonds and the required number of bonds carbon has to have in every compound is 4. Okay, so since we've seen what organic chemistry is, we've seen what organic compound is, we've seen catenation, we've seen the first organic compound be synthesized, we have also seen catenation, right? The next topic we are going to be looking at for is elemental analysis. Remember, organic compound contains elements that makes up the compound. So we need to carry out analysis to be able to ascertain if a compound is organic or not, right? So that is the next topic we are going to be looking at for. All right, so sit back and relax and enjoy. Please subscribe to our channel if you haven't done so. Thank you. Subscribe to our channel if you haven't done so. Thank you. All right, continuation of where we stopped. We want to talk about elemental analysis. Right now, what is the importance of elemental analysis? Recall, let me just give us a quick introduction. Recall, organic compound, we said, contains certain elements. Carbon and hydrogen has to be present for any compound to be called organic. Right, so this analysis is basically analysis carried out to determine if a compound is truly organic compound. Right, so how do we actually verify that? By carrying out elemental analysis. So elemental analysis is analysis to identify the various kinds of elements that is present in an organic compound. All right. So once you carry out this analysis, you can tell if a compound contains carbon, hydrogen, in addition if it has sulfur, nitrogen, halogens, and the rest of them. So the first one is going to be analysis for carbon and hydrogen. Now, analysis for these two elements goes hand in hand, right? They go together. Okay, so in this analysis, all right, a known weight of the organic compound is mixed with a dry copper oxide and heated, all right? So a known weight of the organic compound, presumably containing carbon and hydrogen, we are presuming, all right? We want to verify if truly is going to be, there will be hydrogen or carbon inside. So you're going to take a known weight of the organic compound, okay? A known weight of organic compound, and then mix it with dry copper 2 oxide. Now this is copper 2 oxide. CuO, copper 2 oxide. So this is copper 2 oxide, and then you heat. All right. Now, once you are done heating, what you're going to do now is to carry out a test. Remember, every test for every test, we always have observation and of course inference. So once you do this, you're going to observe something, or you're going to carry out extra step to verify or to confirm the element that is present. So the first one we're going to do is test for carbon. We want to test and see if carbon is present here. So we say test for carbon. All right. Now, how do we test for carbon? Now, listen and listen very carefully. During the heating of all the carbons that are present in that compound will be converted or will be oxidized to CO2. So if carbon is present, carbon will be oxidized using copper oxide. This copper oxide is going to oxidize all the carbons in the organic compounds to CO2. We all know that CO2 is a gas. Now this CO2 will be detected using lime water. CO2 will be detected using lime water, right, which can also be called calcium hydroxide solution, which has a formula of this. All right, so how do we actually detect CO2 using lime water or calcium hydroxide solution? Now, lime water will turn milky, right? We're going to add lime water, or this gas will be made to go through lime water. If the gas that is coming out from that is CO2, CO2 will turn lime water milky. So in the presence of CO2, this lime water will turn milky. Right? Once you see lime water turning milky when a gas enters it, it simply means that that gas is CO2. So how do we actually answer that question? The CO2 in this, which indicates the presence of carbon, because if carbon is present, this copper 2 oxide converts it, oxidizes it to carbon 4 oxide, which is detected using lime water. Lime water turns milky in the presence of CO2, right, which confirms the presence of carbon, because if there is no carbon, there won't be any CO2. And if there is no CO2, this lime water will not turn milky. So the lime water turning milky means there is CO2 coming in contact with that lime water, because once CO2 comes in contact with lime water, it will turn milky, right? So once you see a milky coloration of lime water, it tells you one thing, that CO2 is present, and CO2 cannot be present if there is no carbon. So it simply means that the compound contains carbon. So you have sorted out that of carbon. All right. So let's test for hydrogen. Test for hydrogen. Now, class, all the hydrogens present in the compound will be converted to water. Will be converted to water. So test for hydrogen. All the hydrogens present will be oxidized to water. Remember, carbons will oxidize to CO2 using copper oxide. So all the hydrogens present will be converted to water using this. So how do we detect water? Right? So this is basically what we are going to use to detect water. The water is detected using anhydrous copper sulfate. Now, water is detected using anhydrous copper sulfate, which is white in color. So just follow me so that you understand how this copper sulfate is going to help us understand. By the way, another name for copper sulfate is copper tetraoxosulfate 6, right? Or copper 2 sulfate. So most times they can say copper 2 sulfate because the oxidation state of copper here is +2. So let's get back to this. All the hydrogens will be oxidized to water which is detected using anhydrous copper 2 sulfate, which is white in color. So this particular compound, anhydrous means there's no water. It's just like your salt. Salt is a crystal, right? So this copper 2 sulfate is like salt, like is white in color, right? Now, class, in the presence of water, this copper 2 sulfate is going to turn to blue, right? So once you use copper 2 sulfate on this, and then you see the color changing from white to blue, it simply means that there is the presence of water, because it's only water that will change this from white to blue. So once the color changes from white copper sulfate to blue, it simply means that there is water present in that compound. And if water is present, water can only be present if there is hydrogen, because it is the hydrogen that is present in the compound that will be oxidized to water, which in turn will be detected using copper 2 sulfate. Copper 2 sulfate is white in color, but in the presence of water, it changes to blue. So once you see this copper 2 sulfate changing from white to blue, it simply means that water is present. So we use copper sulfate to detect the presence of water, which in turn tells us, indicates the presence of hydrogen. So once this copper 2 sulfate comes in contact with water, this becomes copper sulfate. Once this is white and this is blue. Once this comes in contact with water, it becomes blue. So the presence of the change of color from white to blue indicates the presence of water, which in turn indicates the presence of hydrogen. So with this particular analysis, you should be expecting, I believe you understand how this is being asked. All right. So in the next video, I'll be making videos to show the various ways question has been asked in the past years, so that it will help you understand better. Okay, so the next analysis we're going to be carrying out is analysis to identify nitrogen, halogens, and sulfur. So we have and halogens. We have Lassine test, which is also known as sodium fusion test. Now, this is a test carried out to identify nitrogen, sulfur, or halogen that may be present in an organic compound. Okay, so like I said, organic compounds comprise of non-metallic atoms coming together to form a compound. So we've seen how we can actually identify for carbon and hydrogen. So we want to test to check if nitrogen is present, sulfur, or halogens. So we're going to actually bring the organic compound, right, and add sodium to it. Fusion simply means bringing together, right? So we're going to fuse this compound with sodium, right? So you bring sodium, you say organic compound plus sodium, and then you heat. Class, any nitrogen that is present in this compound will be converted to cyanide. This is sodium cyanide, but they call it cyanide ion. Class, any sulfur that is present in this compound will be converted to sulfide. We call it sulfide ion. Class, any halogen that is present will be converted to sodium halide. So the big question goes as follows. In exams, they might ask you, in sodium fusion test or in Lassine test, nitrogen is usually converted to dash. Class, nitrogen is always converted to cyanide ion because this compound is ionic. right? Ionic compound, the Na is plus, the Cn is minus. So this is a cyanide ion. And sulfur is always converted to sulfide ion. Now halogen is always converted to halide ion. Okay, so how did we achieve this? I'll take it again. This organic compound comprised of, let's say, carbon, hydrogen, nitrogen, sulfur, halogens. Now these halogens could be chlorine, bromine, or iodine. Now the first analysis we did was for that of carbon and hydrogen, which we did in the previous video, right? Now this time around we want to check out for nitrogen, sulfur, and halogen. So what we are going to do is that we're going to bring this organic compound, mix it with sodium. Why are we mixing it with sodium? Sodium has a positive charge, and each of these elements, so nitrogen has negative charge, sulfur has negative, and halogen will always have negative. So if any one of them is present, right, it will actually be attracted towards this sodium, which is plus. So if nitrogen is present, nitrogen is converted to cyanide ion, cyanide. If sulfur is present, sulfur is converted to sulfide. If halogen is present, it is converted to halide. All right. So once we are done with this, we are now going to start subjecting the product of this analysis to different types of tests. Remember, if you mix this guy with organic compound and you heat, the product you're going to have, you cannot tell if it contains nitrogen, or if it contains sulfur, if it contains halogen. So you're going to take that product and subject it to individual reactions. So for example, I brought 10 liters of water or 10 liters of organic compound. I want to analyze that compound. After mixing it with sodium, right, I will heat. I can now take a portion from that 10 liters and say, okay, let me test for nitrogen. I do a test for that. I'll take a little portion again. Let me test for sulfur and let me test for halogen. So that is basically what we're going to do next. But please take note, in sodium fusion test, nitrogen in organic compound is usually converted to cyanide ion, sulfur is usually converted to sulfide, and halogen is always converted to halide. If the halogen there was chlorine, chlorine will be converted to chloride. If it was bromine, bromine will be converted to bromide. If it was iodine, iodine will be converted to iodide. So since we've actually seen how the sodium fusion test is going to convert all the halogens to halides, all the nitrogen to cyanide, and all the sulfur to sulfide. So the next thing we're going to do is to start carrying out individual tests to identify if truly halogens are present, and if possible, the types of halogens that are present. Now, it is important for me to state this, that Lassine test is a type of qualitative analysis. Remember, we have two types of analysis, qualitative and quantitative. All right, so Lassine test is more or less a qualitative, right, because it tells us the type of element that is present in the organic compound. So the first one we're going to be looking at for is test for halogens. Right, so we want to check if the halogen that is present is chlorine, bromine, or iodine. So how do we go about this? Just sit back and watch us do this. Now, so what we are going to do here is that it says in this method, a known mass of the extract. Now the extract is basically what we got from the sodium fusion test. A known mass of the extract is added to a mixture of concentrated nitric acid, right? So this is, let's assume this is the extract, which contains the halide fused to sodium. So we said a known mass of the extract is added to a mixture of concentrated nitric acid. We have concentrated nitric acid and solid silver nitrate. Right? A known mass of the extract is added to nitric acid and solid silver nitrate. Now, once you do this, the question, we will proceed to say unheated in a glass test tube plus heat. All right. Now, the tube is cooled. You know, when you heat the test tube, it becomes hot. So after mixing all of this, you're going to heat it. All right. After heating it, you cool the tube, right, and transfer the contents inside water. All right. Once you transfer the content inside water, these are the possible products we are going to have. Is either you have chlorine present as a halogen, or you have bromine present, or you have iodine present. All right. Now, all of this is going to be a precipitate. Now, listen, you're not going to get three of them at once. No. Now, these are the possible options because these halogens are this. So it's possible that if chlorine is present in this compound, what we are going to form is AgCl. If bromine is present, what we are going to have is AgBr. And if iodine is present, what we're going to have is AgI. You understand? Now, but how are we going to determine if truly chlorine is the one that is present, or bromine, or iodine? Now, two things we are going to do, or two things will help us to understand or to tell the type of halogen that is present. The first one is the color of the precipitate. Number two is use of ammonium hydroxide solution. So, for us to tell which of the halogen that is present, two things involved: the color of the precipitates and the use of ammonium hydroxide solution. Now remember, three of them here are all precipitates. Now, if chlorine is present, the precipitate color is going to be white. Now, this is white precipitate. Now, if bromine is present, we're going to have pale yellow precipitate. If iodine is present, we're just going to have yellow precipitate. Now, you need to understand that pale yellow and yellow, the difference is that one of them is bright and one of them is faint. Yellow is bright, pale yellow is, is less of being yellow, like is lighter yellow, but yellow means is bright. So in case of exams, you can use yellow and then give us the next part. All right, so like I told us, two things can help us identify which type of halogen is present. The first one is the color of the precipitate. So if chlorine is present, white PPT. If bromine is present, pale yellow PPT. If iodine is present, yellow PPT. So the next thing we're going to use is solubility in ammonium hydroxide. Class, this guy, silver chloride, is soluble in ammonium hydroxide. Please, this is ammonium hydroxide. Ammonium hydroxide or ammonia solution. So this is ammonium hydroxide solution. All right, so we said this is white precipitate, and this white precipitate, this silver chloride, is always soluble in ammonium hydroxide. So in the case of exams, you're being told that a precipitate was formed that is soluble in ammonium hydroxide, even without mentioning the white PPT, right? It is silver chloride. Now, how does this second guy fare inside ammonium hydroxide solution? Now, this is sparingly soluble Now, this is sparingly soluble. Silver bromide is sparingly soluble in ammonium hydroxide. Sparingly simply means it is slightly soluble. Now, this one now is insoluble. in all right. So having said this, let me quickly run a recap on this analysis. Now, this analysis is test for hydrogen. Sodium fission test will actually convert the halogens to sodium halide, but we do not really know the type of halogen that is present, whether it is chlorine, bromine, or iodine. Hence, we are going to carry out test for halogen to identify the type of halogen that is present. So we're going to take the extract, what we got from the last time test or the sodium fission test. We're going to take a little quantity, mix it with sodium nitric acid and silver nitrate. Once you mix three of them together, it becomes a mixture. You heat it inside the test tube, right? Once you're done heating it, you're going to transfer the contents of the test tube inside water, right? Now, it's going to give you a precipitate. If the precipitate that is formed is white in color, it is silver chloride. And this white precipitate, if you dissolve it inside ammonium hydroxide, it is soluble. Now, how about if the color of the precipitate, after you transfer the content into water, is pale yellow or light yellow? That means the precipitate is silver bromide, which indicates the presence of bromine as the halogen. Now, if you dissolve this guy inside ammonium hydroxide, it is sparingly soluble. Sparingly soluble means it is not very soluble, right? But it's still soluble. Now, the last one is silver iodide. If the color of the precipitate is yellow, bright yellow, it tells that the halogen present is iodine. And if you dissolve this precipitate inside ammonium hydroxide, it's going to be insoluble, right? So having said this, I will be giving us, at the end of this topic, I'll be giving us questions, and you can see how the questions were twisted to help us understand this guy better, all right?